All right, so today we're going to take a look at 6.2, which is a section in your textbook called volume by slicing, all right? And when we say volume by slicing, we're going to be slicing in a lot of different shapes. And so it will be important for us to always be thinking like, what shape are we slicing into, okay? And so let's start with what we know, all right? So things that we know so far. We worked on last week, the very last day on Thursday, and we took a look at this idea that if we integrated sort of the length or the height of all of these rectangles, that we would eventually get the area of the entire region that we're looking at. All right. And so this we could say is from 6.1. All right. We're looking at area between curves. And in particular, thinking about if you have sort of two different curves. So let's say you have a curve like this, and then you have a second curve. And if you want to find the area between sort of an A and a B, a starting and an ending point, we have all of these rectangles in between where I want to start counting, where I want to finish counting. And if we find the heights of every single one of these rectangles and we add them together, that's what we call the integral. And that's how we end up with our area between the two curves. And now we did talk a little bit about this decision making, like, for example, how do we know if we're going to have dx, or how do we know if we're going to have dy? And so I'm wondering, before we move on to the what's new, if someone could tell me, based on this diagram that we have right here, are we looking at a dx or a dy situation? Good, good. Yeah, we're looking at a dx situation. And I think the phrase we said is exactly, we're stacking it along the x-axis, meaning that we start here and then we just keep lining up all these rectangles along that x-axis. And so we'll have a dx situation. And if we sort of turned our heads sideways by like 90 degrees, we could imagine that might be a dy situation, okay? So that idea of decision making is definitely going to be important as we move into this next section, all right? And so what's new? Well, turns out that it's all nice to do things and take from one dimension and integrate it and end up in two dimension. But it turns out we can take that one step further, meaning that if we have the area, all right, so if we have an area formula and we integrate it, we're going to end up with volume. Okay. We can do the same thing with respect to y. So we could have the area function with like y's in the equation. We could integrate it with respect to y, and we'll end up with the volume of a certain shape, right? And so if we were to sort of summarize the main point of what we're going to do in 6.2 and 6.3 is that if we integrate a two-dimensional situation, then we end up in three dimensions. Right? So if we integrate in two dimensions, we're going to actually end up in three dimensions. That is where we're going to start our story today. And I do want to preface this by saying that for some people, visualizing is way harder than others. And I want to say that because I was one of those people. It was so hard for me to visualize for a really long time. And it's something I really had to actively work at. And so when you're listening to the lecture, it feels like it comes quote unquote easy to me. I just want to say up front that it wasn't easy in the beginning. It took a lot of time for me to sort of get to this point of where I feel comfortable visualizing. But all of that is to say that if it's something that you sort of consistently work at, it is something that you can improve, okay? So let's get started. Let's take a look at some pictures. So many pictures today. So this first section is called volume by known cross sections, okay? And I'm actually going to go ahead and highlight this volume by known cross sections. And then I'm going to go down and highlight sort of the second part of 6.2, which is what I hope to start a little bit of today, but we'll do primarily a lot of it tomorrow. So volume by known cross section is the first chunk of what we're going to do. All right. So we'll be looking at pictures that are kind of like this. But I'm going to scroll down past a few examples and see where we're going to pick up with the second main topic. Okay. And so the second main topic that we're going to take a look at is something called disk method or washer method. Okay, so the focus for the first part of today is volume by known cross sections. And then if we can start a little bit of the story about disk method, then that's where we're going to start at the end of today. Okay. All right, so let's begin with these pictures. So in every one of these pictures, you'll notice that we have like a three-dimensional shape. And sometimes it's a little bit helpful if we outline certain pieces of this. And so, for example, in the yellow right here, okay, that yellow sort of ovally thing that I just drew is actually an outline of the bottom of the shape. All right, so I want you to sort of like look at that a little bit again and see if you can see that that's the bottom of the shape. All right. And I'm going to go through every shape in the front in this top row, and I'm going to draw in that bottom of the shape. Okay. So for example, in the blue one, I noticed that this right here is the bottom of this three-dimensional shape. And in the yellow picture, I've got this is the bottom of the shape. Okay. So I don't know if people still really have these anymore, but does anyone have a paperweight? Or anybody ever seen a paperweight? Yeah, so a paperweight is basically like this object, a three-dimensional object that basically sits like the bottom of it is flat, so it can sit like flat on your desk, and it's meant to sort of keep papers down on the table or whatever surface you're on so they don't all sort of fly away. Okay, and so all of these shapes could be considered some sort of paperweight in that the bottom part is flat. Okay. But each of these have sort of what we would call different cross sections. And so in particular, the green one, we might notice that out of the bottom, all right, sort of sticking sort of straight out of a table or a flat surface, what shape would we say are each of these slices in the green one? Super close. Can we be a little bit more specific than a circle? Yeah, semicircles, exactly. And so right in here, I'm going to go ahead and write the word semicircle. All right. So each of these slices are semicircles. And now I said we're going to be integrating today, and in particular, we're going to be integrating area. So I'm wondering if you can tell me what the area formula is for a semicircle. Very nice, very nice. Literally the area of a circle, pi r squared, and then we're going to cut it in half because we have a half circle. All right, so area would be pi r squared. That would be a full circle, but we only want a semicircle, so we'll cut it in half. Now, also because we'll be integrating, and we know that life can be easier if we have a constant and we go ahead and pull that out to the front. And so I'm wondering if you can tell me, what are the constants in this equation, the pi r squared over 2? What are the constants? Perfect. The constants are pi over 2. And so if I were to sort of prepare my brain for an integral, I might bring pi over 2 to the front, and then I would have an integral symbol, and then the r squared would be the part that I'm integrating. Okay. All right, so the green one we have is a semicircle. Now, if I look at the blue one, all right, remember the yellow part is sort of the base of the of this paperweight shape. And each of these that I'm outlining in the pink right now would be considered a cross section. And so I'm wondering if you can tell me what shape the blue cross sections are. Yeah, exactly. Half of a semicircle, or we might call that a quarter circle. All right, so we have a quarter circle. And how would we modify our area equation so that we could talk about a quarter circle, right? Because we have a different shape, so we would need a different area formula. Perfect. Pi over 4 r squared. So we have pi r squared, that's the whole circle. We cut it into 4 pieces because we want a quarter circle. And if we, again, prepare our brains for what we want to do, we know we're going to be integrating. We're going to bring those constants, pi over 4, to the front. And then the r squared is going to be the part that we integrate. Right? All right. Yellow ones. Each of these cross sections, right? So each one of these that I'm outlining in the pink, what shape are those? Perfect. We've got some rectangles going on here. And we don't want to say square because we don't know for sure that the base and the height are equal. And so I really appreciate that we're saying it's going to be a rectangle. And if we were to say, here's the area of a rectangle, what equation might we want to use? Exactly. We could say length times width. We could say base times height, whatever our childhood self remembers from all of our geometry experiences, but we know that we're just going to take sort of the bottom part and we're going to multiply it by the height, okay, whatever's sort of coming up and out of the page. All right, I'd like to ask you one more set of questions with these pictures, and then we'll take a look at the second set of pictures, all right? And that question is this. One of the lines that I've drawn sort of the circly outline and the cross section outline, but if we go back, we might notice that there's sort of these lines across the bottom, okay? And what those lines are actually part of the cross section. In other words, here we have sort of, here we have like the bottom of that semicircle. And then this second one back here, that would be like the bottom of that semicircle. And then that's sort of like the bottom of that semicircle. Okay. And so maybe by drawing in the bottom, it helps us see a little bit more that we're looking at something in 3 dimensions. Okay. Now I'm wondering if you can tell me this distance all the way across, does that represent the radius or the diameter? Okay, so this distance across, this is your diameter. And so if I gave you that distance and I wanted you to use it in your area formula, what would you do to that number? Okay, we would have to cut it in half, right? So if the distance that we have represents a diameter, and we want a radius, we're going to have to divide by 2 in order to use it in the equation. Okay. Now let's take a look at the quarter circle one. So the quarter circle one, if I draw on that bottom piece, might look something like that. Or this one goes like this, and this one. Okay. And so maybe by drawing in that bottom piece, we can see it a little bit better, that we have this yellow circle on the bottom. Exactly. Now, if we look at the green picture and the blue picture, the green one, we have a diameter, but the blue one, we have a radius. Okay. And so sometimes we have a diameter and sometimes we have a radius. And in order to tell, we're going to need to be able to look at that picture and establish what that is. All right. So when we were drawing all those lines on Thursday, when we're talking about like, this is the rectangle, this is the height of the rectangle, we're going to continue to draw those lines, but they're now going to mean different things depending on the picture. Okay. Last but not least, if I draw in the bottom part over here, right, I only drew sort of 2 rectangles here, but that base, this part right here, we could say is the base of a rectangle, or maybe we could say it's the length of a rectangle, but it's only one of those letters. Do we have to divide by 2 or anything like that in this yellow case? No, we can just take it as it is, okay? And so as we move into some of those problems that we're going to do, we really want to make sure we know what lines are we drawing and what does it represent. All right. And this idea of if we have a diameter, we better divide by 2 so we can find the radius is going to be really valuable. Knowing this is the base and it's all good. We don't need to divide by 2, or this is the radius. We don't need to divide by 2. We're all set. That's going to be an important decision. Okay. So let's kind of practice our thinking again with this bottom row, all right? And you'll notice that the bottom row, they're all triangles, right? But they're sort of different kind of triangles. And so if we again sort of use this outlining, we can see that in the first picture, here's our base. And maybe one of the first cross sections is this triangle over here. And maybe we could outline another one. All right. Now, if we did the same thing in the second yellow picture, we have our base. And this time we have triangles that are kind of not right triangles. Okay. And so maybe how we describe these is we could say this is a right triangle. Whereas the second yellow picture would be a non-right. And we could also say that that third one, this picture right over here, it's got that circle base again, and we've got triangles. Now, I would say that the red triangles and this middle picture sort of look similar, but maybe we'd say the ones in the right one are a little bit more equilateral, right? That all 3 sides might be the same. Or we could describe those triangles as like the height is taller, right? But there's a certain relationship there. But all 3 of these we could consider to be some sort of triangle situation. And if we're trying to find the area of a triangle, what formula would we use? Good, good. We would say area would be 1/2 base times height. And 1/2 would be our constant. We would bring that to the front of the integral, but base times height, we would keep inside the integral, okay? All right, so let's kind of get all 6 of these pictures on one page just so we can kind of see where we're going to be moving forward. Now, here's the thing. It's easier when we see the pictures, all right? But when we are drawing things and the information that we get in the questions, it's going to be giving us directions in sort of 2 dimensions. And so where our brain power is really going to be going is how do we take something in 2 dimension and draw and imagine what the 3-dimensional part will look like. And in fact, we're going to be basically drawing a lot of these bases. That's going to be the 2-dimensional part that we'll see. The part we will not really see in our drawings is the part that comes out of that page. So whether it be a triangle, a semicircle, a quarter circle, a rectangle, that's not going to be visible in our diagram. And so as such, we're going to label things really carefully. We're going to write a lot of words so that even if it doesn't make sense right now, we can sort of go back and read what it is that we're trying to find, okay? I would encourage you to do this in your practice. I think it will make this last week of content significantly easier if you label all this stuff, okay? So without further ado, let's try our first problem. All right, so this is what a question is going to look like. There's no diagram. It is up to us to draw the diagram, interpret the diagram, come up with an equation, and then at the very end, we get to do an integral, okay? So lots and lots of emphasis on the setup piece of things. Setup meaning we're gonna start with a picture, all right? We're gonna start with a picture. We're gonna be really thoughtful about how we craft that picture and how we label it. We're actually gonna find intersections just like we did last week with 6.1. And we're going to set up an integral, and that integral is actually going to tell us about volume this time, not area. Okay. So example 1, the base of a solid S is in the region of the plane bounded by the parabolas f of x equals x squared minus 3 and g of x equals 5 minus x squared. And so if we say, let's go ahead and draw these, all right? We might want to say these are going to be the 2 different graphs that we have, all right? And we're going to draw these graphs, but what is that space in between the graph, or what's that going to represent? That space that we're going to draw is going to be what the base of our shape looks like. Okay. So in our pictures, we won't see circles, triangles, et cetera, et cetera. But in this case, if we were to imagine things sort of growing out of the screen, this sentence is really important. The cross sections perpendicular to the x-axis are squares. Okay. And our question is, find the volume of the solid. So when we say the cross sections are perpendicular to the x-axis and they're squares, that means that of the 6 pictures we have above, we're imagining something most like the rectangles one. It'll just be a special case where the base and the height are exactly the same. Okay. So let's draw our diagram. All right, so let's get an XY plane going here. All right. Tell me about that red curve, f of x equals x squared minus 3. What do we know about that shape?
Parabola up.
It is a parabola facing up. Tell me more about it. The more specific we can be, the better. Exactly. We are moving that parabola down 3. That minus 3 at the end, that's a clue to tell you you're taking this parabola and shifting it down 3. Okay. All right. What about that green one? 5 minus x squared. What do we know about that green curve? Good. Downward facing. And we know that because of the negative x squared, and it actually is moved up 5 because it's a plus 5, not a minus 5. Okay. So equations actually tell us quite a bit about what that shape is going to look like. And so I don't know how my Monday morning drawing skills are looking, but we're going to draw one parabola here. That's not too bad. And we're going to draw another parabola sort of here. All right, I'll take that for a Monday morning. Okay, so we've got these two parabolas. We might want to label a little bit more. We might want to label that this point here is 0, 5. We might want to label that this point down here is 0, negative 3. Okay. And the last thing I'd like to draw on this diagram for right now is going to be sort of the bottom of my cross section. Okay, so it says here the cross sections are perpendicular to the x-axis. If I draw something like this, are those perpendicular to the x-axis? No. Okay, so if I want to draw something perpendicular to the x-axis, I would be drawing lines like this. Does that make sense? I'm going to draw these lines, and then let's go back and see what those lines stand for. Okay. I would have sort of a very short line here. Make sure that touches. I would have sort of a longer line here. The longest one would be in the middle here. And then I'd have maybe like a medium one here. Okay, and you can draw as many as you want. You can draw them to be more even if you want. But these purple lines right here, all right, let's go back to our diagram for a moment, the one that is actually in 3 dimensions. These purple lines that I drew right here, in our one that is most like the rectangle or square, the rectangle one, that purple line is the same as this, or this, or like this. I love that phrasing right there. Those purple lines here, they represent the base of our square. Okay, I'm not going to draw the squares. I cut and paste these pictures from the internet because I don't want to sit up here and draw a terrible drawing that is so hard for us to see, right? But we can try and make connections between a 3-dimensional image and a 2-dimensional one that we have. And so again, these purple lines right here, because we're looking at square cross sections, that is the base of my square. Okay. So let's go back to our diagram, and we're going to write something here that these purple lines are the base of our squares. Okay. Now, since it's a square, we might also phrase this as the side length of a square. that would also be okay. We want to call it a base of a square. We want to call it the side length of a square. That would be perfectly fine. Okay. All right. So we draw our diagram. It is mostly complete, except, like Matt said earlier, we don't know where these two parabolas cross. So we're going to go ahead and find our intersection points. Okay. Let's go ahead and find those intersection points. The process, no different than what we learned on Friday or Thursday. Okay. We take our red equation, we set it equal to the green equation, and we solve, and that's going to give us our intersection point. In other words, we can take x squared minus 3, and we're going to set that equal to 5 minus x squared. Okay. I see the quadratic. I think, ooh, I better not divide by anything. I'm going to go ahead and move everything to one side, set it equal to 0, and factor. So I'm going to get 2x squared minus 8 equals 0. Good. I see a greatest common factor. I'm going to go ahead and pull out a 2. So I get 2 times x squared minus 4 equals 0. And that will factor into x plus 2 times x minus 2 equals 0. And we'll get x equals negative 2 and x equals positive 2 for our intersection point. All right. If we go back on our diagram, that means we can label this point right here as a negative 2 something, and this point as a positive 2 comma something. All right. You'll see that I kind of leave a space for that y value, but I don't always find that y value because sometimes I don't actually need to find it. All right. If it makes you feel better, you can go ahead and find it. You can plug it back into, you can plug 2 into the red equation or the green equation. You can plug negative 2 into the red equation or the green equation. You can find a y value that goes with it. But as you're going to see, these problems are already so long that sometimes we just don't bother finding the information that we don't need. Okay, that's a hard decision to make up front. So it's okay if you're like, I'm going to find those values first and then call it a day. Okay, so there's no harm in finding that other value, but sometimes you don't need to. So I would maybe wait and see what it looks like first. Okay. All right. So we've got a diagram, we've got intersection points. Now we're going to set up and solve our integral. All right. So where do we even begin? All right. It can be so overwhelming to think about where we're going to begin, but I would encourage you to look at the question. All right. The question says, find the volume of the solid. And if I go back to the very beginning of the notes, we said that volume is the integral of area. Sometimes it's dx, sometimes it's dy. Regardless, volume is equal to the integral of area. All right. Volume is equal to the integral of area. So if you're not sure even what to write for your equation, let's start here. Volume equals the integral of area. Okay. And then we need to start making some decisions. Okay. The first decision we want to make is using our diagram. Do we want to do dx or do we want to do dy? All right. And we can use our diagram. We can use the equations that were given to help us figure out, do we have a lot of equations with x's in them? Do we have a lot of equations with y's in them? All of those same clues from last week are going to be important in figuring out dx or dy. Okay. And so maybe we even think about this like a choice. Which one are we going to do? Okay. Now, if we look at this, all of these purple lines, okay, we are going to start here. We're going to line up all of these bases of the squares, and we are stacking them along the x-axis. Okay. Because we are stacking them along the x-axis, we're going to choose dx. The other clue that we have is that all of our equations are already like an f of x, a g of x. Okay. And so now let's start to set up this integral. We know we need to integrate the area. We've chosen dx. That means that our bounds, like the top and bottom numbers of the integrals, those should be x numbers, not y numbers. Okay, which is kind of nice because we already found x numbers. And so we would want to start, the bottom bound would be at -2 because that's where we start finding the squares. And we're going to go all the way until x equals +2. Okay. Now, I see a good guess, like, do we need to take the integral of f of x minus, or g of x minus f of x, and then we integrate again? And we don't actually have to do a double integral, okay? And so in Calc 3, you explore double and triple integral, all right? We're just staying in the world of a single integral for right now. But all we need to sort of finish setting up this is we need an area formula. If we put an area formula in here and then we integrate, we're going to end up with the volume. Okay. So if we take an area formula and we integrate, we'll end up with volume. And so our final job is to find an area formula. The area formula of what shape? Well, they told us that we had some squares. So we need an area formula for squares. What is the area formula for a square? Good. Area equals base times height. We might even say that it is the base squared or the height squared. No fourth power. I don't know if that was a typo or not, but there's no fourth power. Okay. And so whatever formula, however we choose to represent that, I'm going to say that let's go with base times height for this one. Okay, so if we said base times height dx, all right, I need to think about where the base is and what equation tells me about the base. So for example, this is a base. This is a base, right? This is the longest base. And actually, how long is this longest base? I bet you can give me a number on this one. Ooh, how did we get 8? Someone unpack that process for me. How did we get 8? Good, good, good. Okay. So remember on Thursday, we said if we want to find the area between two curves, we're going to do top curve minus bottom curve, right? And so this one would be 5 minus a -3. 5 minus -3 gives me 8, right? And so to find any base in this entire section, I need to do top curve minus the bottom curve. So when I do top curve minus bottom curve, that will give me the base. How do I get the height? Yeah, in this case, the height is exactly the same as the base because it's a square. And so whatever we write for base, we're going to be able to write that again for the height. Okay. And so we have the integral from -2 to 2. The base will be the green curve, which is 5 minus x squared. Minus x squared minus the bottom curve, which is x squared minus 3. So this, oops, this whole thing, once I simplify it, is going to be the same as the base. Now we said because it's a square, the height is going to be exactly the same as the base. Right, so this height is going to be exactly the same. Now, if it were a rectangle, we wouldn't be able to say that, or we could write it as quantity squared. Either way is fine, okay? But if you're like, oh, how would I do this for a rectangle? For a rectangle, you would need the base and you would need to find the height, right? The square is sort of a special situation. And we're going to take the base and height, make them the same, and then we'll multiply them by each other. Now, one thing I do want to say is in some of the quiz 14s, I noticed that people were not simplifying before they took an integral. And I would really encourage you to simplify before you take the integral. The more you simplify, the easier, the fewer terms you have to integrate, okay? So let's see what I mean by simplify. We've got 5 minus a -3. Okay, that's going to give me 8 minus, and then negative x squared minus x squared gives me -2x squared. This is my base. I know I'm going to get the same thing for the height, so I'm going to go ahead and put a squared right there. So because I have this one and this one, I'm going to say, let's just square it, right? Every year I get someone, at least a few someones who does this. Why would that person be super mad about what they just did? Exactly. All right. This is sad because they forgot to FOIL. Okay, they forgot to multiply out all the terms. Don't be that person. Okay, don't be that person. We do, however, want to multiply everything out. So we'll get 8 times 8, which is 64. That part is fine. But we have negative, let's see, negative 16 minus 16 is negative 32x squared plus 4x to the fourth dx. We actually do know chain rule for integrals. I just don't think we can use it here. What is the chain rule for integrals? Exactly, right? And so we could think maybe we could use u sub. However, I think this is a case where we cannot, because this is our inside function, right? X minus 2x squared. If I think about that derivative, I would need a term on the outside with an x in it, and I don't see that. And so that's sort of maybe a stronger case for why we wouldn't use u sub here, okay? All right, so we've got this. Now, another problem that I noticed on some of the quiz questions was that folks were having a really hard time with the algebra when cranking out the numbers, okay? We want to make sure that we can work well with numbers and fractions and things like that. But we also want to make things easier for ourselves, okay? And so here's one trick that you can use if the conditions are right to make things a little bit easier for ourselves, okay? So let's say that we had a picture like this, right? And I found the volume of like half of it. So I took this shape and I cut it in half and I found half of that volume. How could I find the whole volume without finding the other half? Yeah, right. If I tell you, all right, your salary is going to be half of your salary is going to be $1,000. What's your full salary? It's going to be $2,000, right? So whatever you have, if you have half of something and you know for sure that it is half, you can just double it to find the whole thing. And so if we look at our diagram, all right, we're going to say thank you to the graphing powers that be that my diagram is relatively symmetric here. But we might notice that this part, the right half, is actually the same as the left half, right? Because parabolas are symmetric. They're even functions, meaning that you can fold them along that y-axis, and they're the same. So I'm going to say this. I don't like working with negative numbers because I'm probably going to make a sign mistake. So I only want to find the volume on the right half, and then I'm going to multiply it by 2 to get the entire thing. Okay, that's my reasoning here. I'm going to find half the volume, and then I'm going to double it. How does that change my setup, my integral? If I only want to find half the volume. All right, change the bounds. Change the bounds to what? Good, good, good. Okay, so if we look back at this diagram and I said I want to start here and I want to end here, that means I'm going to start at x equals 0 and I'm going to finish at x equals 2. And so if I go to my equation, I'm going to do this. The integral from 0 to 2 of 64 minus 32x squared plus 4x to the fourth dx. And because the right half is the same as the left half, I'm going to go ahead and double that. All right, so this 2 in the front is using the idea of symmetry to save us some calculating. Okay. All right, now we integrate, all right? But so much of what we're looking for here is, did we get the right setup? All right, some of you on that quiz 14, the setup part didn't match your answers. That's problematic. Okay, so we want to make sure that our setup leads us to that right answer, not just, I'm going to write down the correct answer and then I'm going to sort of make up a setup and hope that it works. Okay, we really want to build this from the ground up. We'll notice that a lot of our integrals are just going to be power rule. They're not going to be too complicated. All right, but power rule means inevitably that we'll have some fractions and things like that to work with. Okay, so we're going to have 2. Integral of 64 is going to be 64x. Integral of negative 32x squared is going to be negative 32x cubed over 3. Plus integral of 4x to the 4th is going to be 4x to the 5th over 5. We're going to plug in 2. We're going to plug in 0. All right. Now, here is why symmetry is so nice. I'm going to plug in 2. I'll get some sort of number situation over here. But what happens when I plug in 0 to all of this? It's going to all go to 0. All right. So I won't have, like when I subtract that second part, that f of a, it's just going to go to 0 and it's going to make my computations a lot easier. What do you mean by divide everything by 4 before plugging in the bounds? Why would we divide by 4? Oh, yeah, we could do that as well. Absolutely, absolutely. So if you notice that we have a common factor, we could in fact factor out that 4, and that would keep these numbers even smaller, right? So yeah, I love that idea. You could certainly do that as well. Okay, so thank you for bringing that up. All right. So I'll leave the actual computations to you, but you should end up with something like this. Okay. All right, so let's get that whole question on one page over here for us. We started with our diagram. We found our intersection points. Again, these two you can sort of do simultaneously, whatever helps you feel like you can draw a better diagram. All right. And then you're going to set up and solve that integral. And you can see that most of what we've written here is really around the setup, not so much around the solving part. Okay. I did want to just point out a really common mistake, not to put it in your heads to make that mistake, but rather the opposite, that we want to just be aware of some typical situations that we want to avoid. Okay. All right. So I think that it is just about 8 o'clock. Let's take a break right now, because I think this is sort of a lot to marinate on. I'd love for us to take a break. We'll go through setting up some more things and talking about the different scenarios. Okay, so let's back at 8:15, and we will work through a bunch more examples and kind of see how far we get. All right, so I'll see you folks back here in 15 minutes. All right, so whoops, let's go ahead and stop the share and reshare. All right, so let's take a look at example number 2. Okay, so example number 2 says compute the volume of the solid whose base is the region between this f of x equals 4 minus x squared and the x-axis. Okay. So we've got two curves again. One of them happens to be an axis, and that's okay. We just need to make sure we draw this, that we label this. And it turns out the cross sections this time are actually perpendicular to the y-axis. All right, the cross sections are perpendicular to the y-axis, and these cross sections are not squares this time. They are a different shape. They are the right isosceles triangles. Okay. And so I'm wondering right now if we can unpack a few things before we even draw our diagram and write down some formulas. Let's sort of do this pre-thinking piece. All right. So tell me what you know about f of x equals 4 minus x squared. It is a downward facing parabola and it's shifted up 4. Good. So we've got this situation and it's going up 4. If we were to describe what the x-axis looks like, what might we say about the x-axis? Good. G of x is equal to 0. And we could even say this is just going to be a horizontal line right on the x-axis. Good, good, good. All right, last little bit of pre-thinking here. I'm wondering if you can tell me an area formula that we might need for the right isosceles triangle. Good. 1/2 base times height. And because this is a isosceles triangle, what do we know about this formula? Like, how can we be even more specific about this formula? I think the hint there lies in the word isosceles, what that means. If you don't know what isosceles means, Google is your friend. This is a good chance to look that up. Good, good. All right, so this right isosceles, because it's isosceles, so base is going to equal height because we know that this is an isosceles right triangle, okay? Well, sort of like our square. We can say that, yeah, we can say that the base is the same as the height. So just like we set up the square equation where we said we have the base and the height, but they're like the same, we can do that same idea here for our right isosceles triangle, okay? All right, all of that is excellent pre-thinking. Let's go ahead and draw our diagram. Okay. So I'm going to go ahead and draw in that x-axis first. So there is my x-axis, and then I know f of x is 4 minus x squared. So I have a downward facing parabola with a vertex at 4. Not so lucky this time. Okay. So we have our downward facing parabola. We might even say that this is 0, 4. And we want to go ahead and draw in those lines, okay? And so this time, we need to read the question really carefully. It says the cross sections are perpendicular to the x-axis. And so if I went and I did this, I would be showing whoever was looking at my work that I didn't really read the question. Okay, so in particular, perpendicular to the y-axis means that we're looking at things like this. Okay. Now, just from the way I've drawn that diagram, are you thinking we should use dx or dy? Good, good. This is important to be able to start to predict that, okay? We are stacking these up the y-axis, and so we are going to be looking at dy. Now, last thing before we move on to finding our intersections, these lines that I just drew, what does it represent? Good. Okay, so this we could say is the base of the right isosceles triangle, right? The base of the right isosceles triangle. And in fact, we can also say this is the height of the triangle because they happen to be the same in this case, all right? But this line itself actually represents the base of that right triangle. And so before we find our intersections, right, we have a very two-dimensional picture here. It is flat on your screen. It is flat on my screen. But if we want to imagine what's happening, it looks like this. And the part that we've drawn is sort of this flat part on the bottom. And then coming out of our screen would be these right isosceles triangles. Okay. And so the lines that we drew represent the base of those triangles. All right, we find our diagram. We need to make sure we find our intersection points as well. It is not different from what we did last week. It is not different from what we did earlier. We would take our f of x, our red curve, we would set it equal to our g of x, or our green curve. And so in this case, it's just 4 minus x squared equals 0. We can say that x squared equals 4, and then x equals plus or minus 2. Okay. And so what does that mean? It means that these points right here, we've got 2 comma something, and we've got -2 comma something. Now, again, I don't want to find more information than I need right now, so I'm just sort of leave this diagram and intersections the way it is right now. We'll see if we need to come back and find anything else, okay? All right, so now we're going to set up and solve our integral. And as is a very good place to start, volume equals the integral of area. We want to choose, are we looking dx or are we looking dy? And based off of what folks said earlier, it seems like dy, because we're stacking along the y-axis, would be a good place to go, okay? And so instead of jumping right to an equation, okay, a part that I think is really important in scaffolding that experience for yourself is writing out in words what you need for that area equation to be, and thinking of using that to help you think about your bounds. So I literally will write 1/2 times base times height. That's the equation that I said I needed. And I've chosen dy. And I've chosen dy, that means that these numbers right here, if I used -2 to 2, that would be showing my reader that I didn't really understand what those bounds stood for. right? If I choose -2 and 2, the problem is those are x values, first of all. Second of all, I'm not stacking this way from -2 to 2, but I'm stacking this way. Exactly. So instead of -2 to 2, our values are going to be from 0 to 4. Okay. And so in this case, it probably would have been beneficial for me to know that this point is actually -2 comma 0 and 2 comma 0. Because what I'm actually finding is I'm starting at this bottom y value and I'm going to that top y value, right? Because I'm going up the y-axis, 0 to 4. And I'm going to add up every single triangle in that region, okay? Now I need to find an equation for the base, and whatever equation I find is going to be the same equation that I can use for the height, all right? But I need to find those. So I know I'm going to need to find the base. So let's think about some numbers, all right? So the longest base would be down here. How long is that base? Good, it's 4. Okay, now let me ask you this. What if I told you that this right here, this point was 1 comma something, and this one would be -1 comma something? How long is that base? 2, good. And what if I picked one more value? I said this was 1.5 comma something, and this was -1.5 comma something. How long is this base? 3. Okay. How long is just this part? 1. Okay. And 1 times 2 will give me 2. How long is this part? 1.5. Okay. And what's 2 times 1.5? 3. Okay. Let's say this was 1.75. If I doubled it, I would get the whole base, right? And this length we said is 2. And if I double that, I'll get 4. Okay. Now, this idea of doubling sometimes comes up in symmetry and sometimes comes up when we're writing equations. I love what someone said earlier about left or right curve minus left curve, right? Because when we're looking at the base and we're going sort of horizontally, we want to say for dy, we're going to do the right curve minus the left curve. Okay. But our equations are all like f of x equals a bunch of things with x's, and that's not really convenient for that. And so what we're going to do is we're actually going to take our intersection, we're going to move that over a little bit. We're going to add like a 2.5 situation, okay? And so sometimes you're going to have to do a little bit of rewriting. And so we have y equals 4 minus x squared, right? We have y equals 4 minus x squared, but that is like an equation with x's in it. So if I want to write an equation with y's in it, I'm going to go ahead and take this equation and I'm going to solve for x. I'm going to get x by itself. And when I do that, I get x squared equals 4 minus y. But in order to go ahead and isolate the x, I'm going to need to take the square root, and I'll get x equals square root of 4 minus y. Now, I think this class has been particularly good about remembering that there is a plus minus in front of there. Okay. It hasn't always mattered in the past, but if you want to find a right curve and a left curve, you better have two curves, right? So all of a sudden, forgetting a plus minus means you're forgetting you have a whole nother curve. And in fact, the positive square root of 4 minus y corresponds to the right half of this parabola. And the negative square root of 4 minus y corresponds to the left half. And so by remembering that plus minus, we actually have our right curve and our left curve. Okay. So here's what we're going to do. We're going to go to our equation. We're going to say we have a few things. 1/2 is a constant. I'm going to bring that out to the front. The integral from 0 to 4. The base is going to be the positive square root of 4 minus y minus the negative square root of 4 minus y. So positive square root of 4 minus y minus the negative square root of 4 minus y. Because that is right curve minus left curve. Because we said this is an isosceles right triangle, the height is exactly the same. Right curve minus left curve. Okay. So before we continue with the algebra and things, at this point, we are primarily done with the setup. And so I want to pause here for a moment and just see if there are any questions that are coming up about how we got certain things or where things went or why we're making certain decisions. All right. It's okay if those questions come up later, but as you are working on quiz 15, we want to think about, are we okay on the setup? Okay, that is the most important part. The most important part is that setup piece. All right. So if you feel like you've been missing points on certain things, you're not sure why, a lot of it boils down to that setup. I don't care if your answer is right. If it's a magical answer and it does not match your work, it means very little to me. Okay. I want to make sure we know how to make these decisions. All right. Once we've set this up, we're going to do a lot of simplifying here. We'll have our 1/2, the integral from 0 to 4. All right, what does this in the darker purple simplify to? Good. I'm going to end up with, whoa, I'm going to end up with 2 square root of 4 minus y. And I'm going to go ahead and say I'm squaring that because I have this base and that height, which together make the square part. Okay. All right, we're going to do a little bit more simplifying here. If I go ahead and bring this 2 out to the front right now, what mistake did I make? I didn't square it, right? That 2 has to be squared. The square root of 4 minus y has to be squared, right? Everything in there has to be squared. And so I get 1/2 the integral from 0 to 4 of 4 times 4 minus y. Okay, so I have to distribute that square. Once I've distributed it, now I can bring that 4 to the outside, to the integral from 0 to 4 of 4 minus y dy. And that might be one of the nicest integrals that we've seen in a long time. And when you work through this computationally, you should end up with 16. Okay, but here it is all on one screen for you. All right, so we have our diagram, we have our intersections. We went to step 3, set up and solve the integral, but in order to do that, we actually had to go back and do a little bit more algebra. Okay, so even though these are like steps 1, 2, and 3, there might be like a step 2.5, or maybe we need to go back and forth between step 1 and step 2, and that's okay. And the fluidity to be able to do that really comes from understanding how to make those decisions. Okay. All right, I think we're gonna do one more example here. And then let's see. All right, so we got a little bit of a lag. All right, it's better. All right, so example 3, okay? This solid has a base in the form of an ellipse. An ellipse that is x squared over 25 plus y squared over 16 equals 1. The question says, find the volume if every cross-section perpendicular to the x-axis is a rectangle whose height is 3 times the base. All right, so I wanted to include this question on here because in pre-calculus, you saw conic sections, okay? So conic sections of pre-calculus, which include circles, ellipses, hyperbolas, parabolas. Now, I wish that in addition to saying these are the classes that you need to take and, you know, in what order, we sort of laid it out for you a little bit more in terms of this is when it's going to come up again. Because sometimes we hit a topic and we're like, ooh, I don't like this topic. I just won't really learn it. And then it'll never come up again and I'll be fine. And that would be a very naive way to approach this situation. Okay, so conic sections. Sections come up again in Calc 2. All right. There is a ton of algebra and in Calc 2 as well. But conic sections are going to come up again. You're going to do a lot of heavy algebra, a lot more integrals and derivatives with conic sections. So I wanted to use this problem as a springboard to remind your brain of what a conic section is and what those equations tend to look like. Okay, so if Calc 2 is in your fall semester schedule, just be aware that conic sections will come up again in that class. All right, so because it's probably been a while since you've seen a conic section, let's unpack this equation together. Okay, so this equation is a very typical standard form for an ellipse. This particular ellipse has a center at 0, 0. And I know this because it's x squared on the top, which is really like x minus 0 squared. And this is y squared, which is really like y minus 0 squared. Okay. Additionally, I know that the 25 below the x means plus or minus 5 in the x direction from the center. So it is not the 25, but it's rather the square root of that number. And so similarly, this 16 down here is really plus or minus 4 in the y direction. And I know it's in the y direction because it's under the y squared. And I know the 5 is in the x direction because it's underneath the x squared. And I'm going 5 out to the side and 4 up and down from my center. Okay. And so that allows me to go ahead and sketch a graph. And so we go ahead and we draw our axes. And we're going to go ahead and draw that ellipse. And so here's my center. I'm going to go 5 out in the X direction. I'm going to go 4 out in the Y direction. And I'll end up with an ovally sort of situation. Okay. So just like, you know, this is a parabola, I know it's facing up, I know it's moved this many units down or up. If you can walk into Calc 2 saying, I know how to do the same thing with ellipses and hyperbolas, you'll be able to have more brain power for the calculus part, okay? And so let's go ahead and write down some of these coordinates before we move on. So we've got 5, 0, this is negative, or 0, -4. This is -5, 0, and this is 0, 4. Okay. And let's go ahead and draw in our cross sections. And so in particular, this one has volume. Every cross section is perpendicular to the x-axis. So I want to be drawing them this way. Okay. What is the longest base that we have to our rectangle here? Good. That longest one is going to be right in the middle here. But I could have like a teeny tiny base out here, like a medium base out here, another teeny tiny one out here. But all of these lines, they represent the base of a rectangle. They represent the base of a rectangle. Now, in all the other questions, the base has been exactly the same as the height, right? We had a square, we had an isosceles triangle. Is this base going to be the same as the height? No, but we do know the relationship. Exactly, all right? So we might want to say here that height is going to equal 3 times the base. All right, great job with the pre-thinking. Let's continue. Let's think about our intersections. All right, now in this case, I would say we don't really need to find the intersections because we only have one curve. My screen is freezing. Okay, we only have one curve. And so it's really more about finding out the X and Y intercepts here. And we were able to find that from the equation. Okay. So I would say that this is NA, not applicable here. And it's okay for some steps to not be done. All right. Depending on the information, we may or may not need it all. All right. So we're going to set up and solve this integral. A really good way to show someone you understand what you're doing is to say, I'm finding the integral of area. And I know that if I find the integral of area, I will be able to find the volume. We can write out our usual choices, dx or dy. What are our thoughts here? Good. We're going to use dx, okay? We're going to use dx because we are stacking along that x-axis. And so let's begin. We have our integral. Our area formula here is going to be base times height dx. Yes, we are going to use symmetry. Let's set it up as if we were not going to use symmetry and then show the simplified step where we would use symmetry. Okay. What would my bounds be in this case if I was not going to take advantage of symmetry? Good. I would start at -5 and I would stop counting at x equals +5. So -5 to +5. Okay. Now you can do this. You can say, I'm just going to use -5 to +5. That is absolutely fine. Okay. Someone asked that question earlier. Totally valid. But if you're sitting there during a timed exam or you just don't want to spend as much time working through a problem, if you take advantage of the symmetry, that will usually make your computations go a lot faster. Okay. So what I mean by that is we could say the 2 times the integral from 0 to 5 of base. And I'm going to go ahead and change height to 3 times the base. Okay. So we're using the symmetry, which is why we're doubling and we're changing that bottom bound to the midpoint. Base still stays base, but the height is 3 times the base. Okay. And so I'm actually going to bring that 3 all the way out to the front as well. So my new coefficient will be a 6, the integral from 0 to 5. Now I see that I'm going to have a base times a base. So I'm just going to write that as base squared. Okay, perfect. All right. Let's figure out our equation now. Based on what I have up here, this x squared over 25 plus y squared over 16 equals 1, I'm guessing I'm going to need like a step 2.5, where we're going to find the equations. Okay. So my equation that I have is x squared over 25 plus y squared over 16 equals 1. Which variable do I want to solve for? Yes, I want to get y by itself. Okay. We want to get y by itself so that we have an equation with x's so that we will match our dx. Okay. So I'll tell you what, I don't like fractions. I really don't. And I wish, I mean, I like what they do for us mathematically, but working with them sort of is sometimes more cumbersome than I would like it to be. Okay, so there's sort of a few ways that we can skirt this. And one of those ways is exactly what Matt said. We can multiply by that lowest common denominator. And so in fact, I'm going to multiply through by 400. That's going to give me 16x squared plus 25y squared equals 400. All right, so presto bingo, I multiplied through everything on both sides, so I didn't change anything. And now I don't have any more fractions. Okay. I'm going to solve for y. So I'm going to have 25y squared equals 400 minus 16x squared. I'm going to divide by 25, and then I'm going to take the square root. And when I take my square root, I want to be like, you folks have been so good about this. I got to remember that plus minus. Plus minus the square root of 400 minus 16x squared over 25. Okay. So this is another good exercise, another good moment where it's like, why do we care if we have a plus or minus in our square root? Because it turns out that the plus equation gives us the top part of the ellipse, and the minus equation gives us the bottom part. So if we don't have both of them, then we don't have our ellipse. We only have half of our shape. Okay, so the plus minus carries a little bit more weight here. Now I'm going to write down one of the most common mistakes that I've seen. What's wrong with that? Exactly. Okay. Now here's the deal. I could take the square root of each part if I made one very small change. If I change this minus to a multiplication, that red answer would now be green. But it has to be a multiplication. All right. Multiplication and division, you can just square root every single part. That's fine. But the moment you have a plus or minus, the rules are different and we have to respect that. Okay. So don't panic about this square root, because up until now, square roots have actually been like a pain in our rear end, that when we have square roots, we got to do like, you know, the power rule with the fraction, and it's like a very big problem. However, we want to take the base and we want to square it. So our square root is actually really nice, because when we square a square root, we end up with just the thing on the inside. Okay. And so what is that base, right? We're going to have to take top curve minus the bottom curve. In other words, we'll have positive square root of blah, 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 minus the negative square root of whatever that expression is. That is, we're going to have square root 400 minus 16x squared over 25 minus the negative 400 minus 16x squared over 25. Good. All right, so that's an important pattern to notice. This minus minus is going to make it a plus. And when I have something plus itself, I'm just going to have two of them. All right, let's go on a little bit more with the algebra. 2 squared is going to give me 4. 4 times no more square root, because I've squared it. Okay. I thought I read the rip out as RIP. Yes, RIP the constants too. You're going to bring all those constants out to the front. Keep your numbers as small as possible. So I'm going to go ahead and bring the 4 out. I'm going to bring the 25 out. And I think we can pull out another 16, something like that. 6 times 4 over 25. 16, is it? I think so. Integral from 0 to 5 of 25 minus x squared dx. Right? This way, you don't have to deal with fractions. The integral of 25 minus x squared, I know you can do that. I know you can plug in 5. You're going to plug in 0, that part's going to go away. So you'll end up with a really large number. But all the work that we've done right here minimizes the computations you actually need to do by hand. Okay. That is sort of we're at an important juncture in your mathematical career where it's not necessarily about how much you can grind through a problem. It's more about how can you be clever about that problem and setting things up so you don't have as many computations to deal with. Okay. It isn't wrong to do it the long way. It will just be longer. Okay. And sometimes we need to do things the long way before we realize, oh, this is a good shortcut. Maybe now let me try that. Okay. So this is going to depend on where you are. If you don't feel ready to jump to all of these sort of simplifications, you can grind through. There's nothing wrong with taking this integral. All right. I think it just takes a little bit more work, but maybe that's what you in particular need at this point, and that's okay. Okay. So here is example 3, all on one page for you. All right. So here's what I'd like to do. We're going to take a look at one more example. We're going to have, I think, a few minutes to start to talk about the story for tomorrow. And the assignment that is due today, the one about watching that video for the visualization, I think we'll sort of start to get that in our brains. And then tomorrow we'll be able to hit the ground running with that second part of 6.2. Okay. All right. So here is the last example that I'd like to do. Example 5, find the volume of the solid whose base is bounded by the circle x squared plus y squared equals 4. And so if we think about this x squared plus y squared equals 4, right? As I mentioned in example 3, conic sections, I think that's actually a duplicate. I think example 4 is actually the same as example 3. And this might actually be the 3rd semester in a row that I've made that mistake and haven't corrected it yet. So, yep. Every time I get here, I'm like, I really should delete that. And then I don't. But all right. So circles are considered conic sections. And in fact, circles are just special cases of the ellipse. It's an ellipse that is not really ovally. In fact, it is perfectly even on all sides. And so this is a circle that has a center at the origin, right? And same reason as before, it's x minus 0 squared and y minus 0 squared. And then our radius of our circle is actually the square root of 4 or 2. All right. So if you see a circle equation in this form, the number on the other side, that doesn't give you the radius, it gives you the radius squared. All right. So as long as you take the square root of that number, you'll end up with the radius. All right. So there are cross sections that are perpendicular to the x-axis, and we have semicircles this time. Okay. So semicircles, we said that area formula was pi over 2 times r squared, right? We can write pi r squared over 2, but knowing we're going to have constants, we want to rip them out to the front of the integral, we'll just keep that pi over 2 in the front. And we'll go ahead and start with our diagram. I know that there's sort of a lot of unideal factors in terms of online classes. But I think one of the things that I will genuinely miss, or maybe I should figure out how to bring into the classroom, is like this notes on a tablet idea. I feel like my notes are so much neater and organized, but also a lot easier to share with students. So I don't know if you have any ideas around that, let me know. Also, look at what it does, makes my circle so perfect. Okay. So we know the radius of our circles 2. And so that allows us to say that these 4 points are ones that we know. This is 2, 0, 0, 2, negative 2, 0, and 0, negative 2. And we're going to draw in that purple line. All of our purple lines will be perpendicular to the x-axis. Oh, really? That would actually, because when I'm in the classroom, I get a ton of marker like all over my hand. Like my hands are permanently dirty from all the marker. So I would actually kind of really like that. All right. We're drawing things perpendicular to the x-axis. I have a tiny semicircle on this end. It's not really straight. Maybe like this. Yep, vertical lines. We're already thinking let's use dx, right? I have maybe like a longer piece right here. The longest piece is in the middle. So patterns that we're sort of familiar with. All right, what does this purple line represent though? That is where we need to make sure we know. Good, this is the diameter of the semicircle. Okay, so this is like that very first green picture that we looked at. We've got the diameter of our semicircle. And so maybe a note that we want to make to ourselves is diameter over 2 will give us the radius. Intersections, I think we can again say that this is sort of not as applicable for this one because we only have one curve. We're not looking at two different curves. We're looking at one curve. And because of the equation format, we were actually able to label those important parts. Okay. I think we will need a 2.5 step though. Okay. And so for those of us who are maybe more linear thinkers and are uncomfortable with how I sort of hop around from place to place, if we're already thinking vertical lines means use dx, what variable should we isolate in our equation? Exactly. We're going to solve for y, right? We're already thinking vertical lines means dx, and dx means our equation should be a y equals situation. So y squared equals 4 minus x squared, y equals, whoa, plus minus square root of 4 minus x squared. If you continue to simplify to 2 minus x, listen, that can't happen. Okay, it can't happen. I know that things do happen, but we are at this point where there's not a lot of forgiveness for mistakes like this. It is totally illegal. Okay. All right. So we've got our plus minus. Like before, we've got the plus that gets sort of the top half of our circle. And then we've got the minus, which gives us the bottom half of the circle. Okay. Let's set up and solve that integral. We're going to say volume equals the integral of area. We've already decided, because of these vertical lines, that we are going to be stacking along the x-axis, and therefore it will be dx. And so I'm going to write the integral from -2 to 2. Being really careful to note that there's a lot of -2's and 2's on my diagram, but in particular, it is the ones in the green. Okay, so the -2 and 2 do not refer to this -2 and that +2. Okay. All right, I need to use my area formula. Pi over 2 radius squared. All right. Pi over 2 can come out to the front. That is not a big deal. Can we use symmetry here? Is that an option for those of us who might want that? Yes, yes, we can, right? In fact, we can say, I'm just going to find the collection of volume on this right-hand side. That'll be from 0 to 2, right? Because 0 to 2. And then whatever I get, I'm going to double it. So I'm going to say 2 times, bring that constant out, from 0 to 2 of the radius squared. Okay. Now, I know that this 2 and this 2 are going to reduce. But sometimes when we just jump to writing a pi in the front, we get confused about where the half went or where the 2 went. Okay. All right. What are our thoughts on the radius? How do we find the radius? Okay, so the biggest radius would be here. It wouldn't be 4, but it would be 2. But I don't want it in general or a specific one. I want like in general for every single one of these. How do I find that radius? Okay. And so here's what we're going to do. We're kind of going to do this the same way we've set up everything else, right? Top function minus bottom function gives us the diameter. And then whatever I get, I'm going to cut it in half to get the radius. Exactly. Okay. So pi, the integral from 0 to 2. My top function is square root of 4 minus x minus the bottom function, which is negative square root of 4 minus x, all over 2. Right? So on the top is my diameter, on the bottom, cutting it in half makes it the radius. I'm going to square it, dx. Now, Luca pointed out a really nice pattern earlier, mentioned that when we have the square root of something minus the negative of that square root, we actually end up with 2 of the positive ones. Which is really nice because this 2 and that 2 will reduce. And so this is actually the integral that we need to worry about. And I think I dropped a squared along the way here. Squared, squared. Okay. All right. So for some reason, I don't actually have an answer for this one. But you can always check your answers with online calculators. There are plenty of online calculators that will help you double check your answers, all right? But the actual integral, like the actual, let me find the integral part is usually not that bad. Most, I would say 90% of the work is in the setup that comes before that line. Like all of this takes up space, right? Space in our brains, space on our paper. But all of that is really where the work is, making sure that setup is going to be accurate. Okay. I will tell you now that on Thursday's exam, I am going to be looking for your ability to set up explicitly like this and show me where things come from. I am less concerned that you can integrate this. Because if you can't integrate that, you probably dropped the class a while ago. Okay, so I trust you to do this part, but the part that I really want us to develop is that decision-making piece. All right, so we've got about 15 minutes left. And what I would like to do is briefly begin talking about this 16 pi over 3. That sounds about right. So if you are planning on trying that question later, maybe write down that 16 pi over 3 just as a potential reference point to see whether that's your answer. Okay. All right. So how many people in here like donuts? Does anybody like donuts? I don't know if anybody likes donuts as much as I do, but. All right. What are people's favorite kinds of donuts? Throw them in the chat. What's your favorite kind of donut? Ooh, anything with coconut, an apple fritter, a chocolate donut, like chocolate glazed, maple bars, solid choice. Oh, okay, nice, nice. Just bread. All right, all right. So my favorite is a jelly donut. I do quite enjoy the jelly donut situation. But I also like a plain, like an old fashioned one is actually not too bad either. Sometimes you just need that to balance out, you know, the sweet and not overly sweet situation. But anyway, why does all of this matter? Well, there's a method that we're going to learn tomorrow, something called the disc method, but it's also known as the washer method. And I don't know about you, but when I think of the word washer, the first thing that comes to mind is like a washing machine. And nowadays we have sort of this, like, we have like the front loading washers, which is a little bit easier to see. But it turns out that the washer doesn't necessarily relate to a washing machine, but we could sort of imagine that we have like this situation. All right, so that part that I sort of highlighted in the yellow is kind of like this situation. We might think of this as a regular donut. Okay. But then we might also encounter some filled donuts, meaning that that donut hole didn't get taken out. It's solid, just like my favorite jelly donut, right? There's some sort of filling on the inside. There's not this space where there could be more donut on the inside. It's not a regular one, but there's a filled one. And so when we're thinking about the disc method or the washer method, one of the things that we should naturally be kind of asking ourselves is, when would we use these methods? And it turns out that there's a very special case of cross sections. In particular, we want to be looking at what happens when cross sections are circles. So no triangles, no rectangles, no squares, no semicircles, no quarter circles. We literally mean an entire circle, okay, a full circle. And if we're thinking a full circle, the equation we really want to have in our brains is area equals pi r squared, okay? And in fact, we could say that for a filled donut situation, we could say area is pi r squared. But how would we modify that equation for area for this regular donut picture in the middle? Yeah, we would find like the big area, and we would, if we were thinking about donuts, we would take out that donut hole, right? We would remove that smaller circle. And so we could say area equals pi big R squared minus pi little r squared. Okay. Now, sometimes we actually say, we don't want to write pi so many times. So we factor out that pi. And we write it as pi times big R squared minus little r squared. Okay, and that again is preparing us for the idea that we're just going to rip those constants out to the front. So let's get that constant. Let's see what that is and bring that out to the front. Just like we did pi over 2, just like we did with the 3 in that one problem. Any constant, we sort of want to say, let's keep our numbers smaller. Let's be more efficient mathematicians and just bring that out to the front. Okay. Now, why would they actually call this the washer method? So let's address that. Anybody ever go to IKEA and then like build their own furniture? I like doing that. Sadly, I find so much joy. Oh, all right. Well, we're all different people, but you have, they package everything into this box for you. You like pour out all the contents, and sometimes, you open up the package of like things that will help you connect them. You'll end up with like a bunch of screws or maybe that hex wrench or some bolts. But there is something called a washer. And I don't know that this is as common in terms of IKEA furniture, but sometimes you'll look in the package and you'll see like a flat disc like this. And you kind of put it like against, like underneath the bolt so that it doesn't rub against the wood that you have there. But that piece is called a washer. And when they named this the washer method, they were referring to like the kind that helps you build furniture, not the kind that helps you clean your laundry. Okay, so that's sort of the background of where this washer method came from. They're talking about something that is actually very similar to a regular donut. Okay, so washer is kind of like a regular donut situation. But where are we going to be going with this story? All right, we're looking at cross sections that are circles. And so let's take a look at some pictures. Okay. So if you have something called an axis of revolution, which you'll be able to see in the video that I asked you to watch, okay? So if you have your axis of revolution, let's imagine those rectangles that we were looking at. And if we took this rectangle and we spun it around the axis of revolution, like it was coming out of the screen at you and then going back into the screen behind your computer, you would end up with a disc. All right. Now in the video, this is more animated. This is a very static diagram here, but in the video, it is animated. And so you get to see things spin around an axis. Okay. Now, notice that when I spin this rectangle around the axis, I end up with, would you call this similar to a regular donut or a filled donut? Yeah, it's like a filled donut. So when people refer to this disc method, okay, this is really more like a filled donut, meaning that there's no hole. You get more sugar, more bang for your buck, okay? Now, let's imagine that we took all those rectangles that we had, those super, super skinny rectangles from when we were finding area. And we took every single skinny rectangle and we revolved it around the x-axis or whatever that axis of revolution is. You would end up with a bunch of circles. And with all of these circles, you would be able to add them all up together to find the volume. Okay. This W, as they call it in the diagram, is really our dx or our dy, because we're assuming that these rectangles are as skinny as possible. Okay. Now, one last note about this diagram. This is our axis of revolution, and it is the same as that. So this axis of revolution sort of goes right through the middle of your resulting picture. Okay. And so what I want to start to do is just have you visualize this, okay? So take the time to watch the video today. Watch it as many times as you want. Look for other videos that might show that animation, or maybe just even Google disc method or washer method. But knowing that we're in sort of our last week and we're in a time crunch, the more you can sort of start to think about this before you come into class. And I don't mean teach yourself. I mean, get your brain ready to absorb what we're going to be learning in class. I think the more successful you will be this week. Okay. And so we're going to stop the video there for today.